What kinds of homework questions do you have today? Anybody have questions to go over? Okay, then let's continue on at 8.1. We're looking at some scenarios involving chance that confound our intuition. So the next question that we have is the question the author opens the section with. He says, how many people are needed in a room so that the probability that there are two people whose birthdays are the same day is roughly 0.9? How many people are needed in a room so that the probability that there are two people whose birthdays are the same day is roughly 0.9? Did you write down an answer, what you thought last class? Anybody remember? I can't remember if we did or if we just went right. Okay, so write down what you think it'll be, okay? So we looked at the pigeonhole principle in chapter 2. How many people have to be in a room to be sure that we're going to have a shared birthday? We could have a shared birthday with 2, and if we wanted to be sure there was a shared birthday, how many people did the pigeonhole principle say that needed to be in the room to be sure we would have a
366.
366. I think one more because of leap year. So 367 because of leap year. Okay, then there'd be possibly one on every day, but on one day there would have to be 2. Okay, so write down how many people you think are in the room so that the probability that there are 2 people whose birthdays are the same is roughly 0.9. And then we're going to do an experiment and see if we can simulate having, I'd like to get a simulation of 40 people in a room, but we don't have 40 here. So let me count how many are here. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19. 19 with me, that's 38. Okay, I'd like to have a simulation of 40 people. So we'll start with everybody writing down their birth date, not the year, just the day and the month. And then someone else that you know, and I'm just going to pick random. So if you know your dad's birthday, write that down. If you don't know your dad's birthday, write your mother's down, okay? So you're going to write my birthday down. Okay, I expect a lot of greeting cards this year, okay? All right, no, just kidding. And then your dad's or your mom's. I'm going to put my dad's down. Okay. So that will represent 38. And I need 2 people to put down one more date. So you could put the other parent down. Who volunteers to be responsible for 3 days instead of just 2? Yep, okay, got 1 there, and I need 1 more. Okay, great. So you write down 3 dates. Now we're going to go through and see if the people represented by 40 of us have a shared birthday. Because actually the probability of a shared birthday is 90%. We'd actually write that as 0.9 with 40 people. So the probability of having a shared birthday is actually 90% with just 40 people. So let's try that experiment and see if we confirm that here. Sometimes we do and sometimes we don't. Actually, I'd say about 90% of the time we do. Okay, so here's how we do it. Who's got a birthday on the 1st of the month, or who's got it written down the 1st of a month? Anybody on the 1st? Raise your hand if you do. 1? Any more? Okay, then you're the only one. 2nd, who's got a birthday on the 2nd? 1? Anybody else on the 2nd? Okay, what month? March? February. Okay, so that's the same. 3rd, who's got a birthday on the 3rd? 1? Anybody else? Okay, then not the 3rd. How about the 4th? Anybody else? Nobody? Okay, 5th? Anybody have a birthday on the 5th of the month? Okay, 6th? Okay, 1 here. Anybody else have one on the 6th? Okay, 7th? Who's got a birthday on the 7th written down? All right, 8th. Okay, 3 people on the 8th. What month is yours? June? March? December. Okay, not on the 8th then. How about on the 9th? Okay, 3 on the 9th. What month? July? May? December. Okay, not the 9th then. 10th? Who has a birthday on the 10th? Written down. Okay, 11th? Yep, one on the 11th. Anybody else on the 11th? Okay. 12th? 13th? Who has a birthday on the 13th? Who has a birthday written down on the 14th? Okay, 2 on the 14th. What month? July? October. Don't I have one on the 14th? Yeah, okay, so we had 2 birthdays then, July 14th. I should have just asked right off the bat. So yeah, if you have a big party over with 40 people, you can certainly run that by and feel free to bet. But remember, it's 90% probability. Now that seems kind of weird, right? Because you'd think there's 367 to be sure of a birthday, so you'd think you'd need 90% of that. Did anybody put around 330 people that they thought? Because that would be, I would think that if I had not looked at this myself. But it turns out that actually 40 people in the room, not 330. So we're going to look at that closely in 8.2 and see why that is. I'd like to look at another scenario in 8.1. The Price is Right scenario. We looked at that in chapter 1 as a silly story. I don't know if all of you read that one though, because you had to pick your silly stories to read. So let's take a look at that together. So this is a scenario from chapter 1 that actually leads to this section. Let's make a deal, Monty Hall enthuses, to the gentleman dressed as a giant singing raisin. The gleeful raisin, whose name is Warren Peace, is ready to wheel and deal as Monty Hall explains the game. Behind one of these 3 doors is the Cadillac of your dreams. It is as long as his train and comes complete with a jacuzzi. Of course, if you spend too much time in the jacuzzi, your skin will wrinkle. But hey, you're a raisin, your skin's already wrinkled. Monty Hall continues by warning that behind the other doors, however, are 2 other modes of transportation, 2 old pack mules. They don't come with jacuzzis, although given their exotic odor, you may want to give them a bath. Of course, the crowd is laughing and applauding, just as the studio sign instructs. I need some signs like that. Monty sums it up. So there are 3 closed doors. Behind one is a luxurious car, and behind the other 2 are mules. Now comes the moment of truth. What door do you pick? The audience erupts. Take door number 1, take door number 1. Door number 2, door number 2. Door number 3 is the one, choose 3. Poor Warren Peace looks around at the crowd, confused and nervous. He considers door number 1, then 2, then 3. Finally, Monty prompts, okay, Warren, which do you want? The raisin-clad Warren shouts, okay, I'll take door number 3, door number 3. As Monty Hall quiets the overly excited audience, he tells Warren, I'll tell you what I'm going to do. I'm going to show you what's behind one of the doors you didn't pick. Let's take a look at what's behind door number 2. With that, Monty Hall turns to the Vanna White of the 1960s and says, please show us what is behind door number 2. The door dramatically swings open, the audience erupts, and Warren breathes once more. Behind door number 2 is a mule. Monty, knowing where the mules are, always opens one of the mule doors first. Monty continues, now we see that the Cadillac is not behind door number 2. You guessed door number 3. I'll tell you what I'm going to do. If you want, I'll let you change your mind and choose door number 1 instead. It's up to you. Do you want to stick with your original choice, or do you want to switch? The audience goes nuts. Stick, y'all have. Switch. Advise the others. What to do. Well, we're going to see what to do in class today. We're going to simulate this situation and see which is the better choice. So we have two scenarios, okay? So we have three doors. There's two mules and one Cadillac. Behind those three doors. So the raisin chooses door 3, and then Monty opens the door, another door, and reveals a mule. So then Monty says, do you want to switch? Or stay with the door that he's chosen? So write down, what do you think the odds of winning are, or the probability of winning? Staying with door 3, or the probability of winning switching. Okay, so switching door is to, of course, the unopened door. You wouldn't choose the one that opened and had a mule behind it. So go ahead and write down what the probability is that you think. Excuse me. Well, we're going to use our cards to simulate this scenario. We're going to try and do a lot of a lot of scenarios with it and see if we can come to a conclusion of which is better, to stay or switch. So if you have your deck of cards with you, that would be great. You'll need to play in pairs because one of you is going to be Monty and one of you is going to be the raisin. And we're going to try both ways, switching and staying. So the ace will be the Cadillac, and then we'll pick a couple of low cards to be mules. So I'll pick deuces for the mule, or twos. Here's another ace. Okay, I'll pick out some extra ones here. So we're going to have switch or stay. So you're going to need to keep a tally. So first you're going to have stay. First you're going to have to stay with the original and record the wins or losses. And then you're going to have switch. And record the wins or losses. Now for both of these, the dealer, Monty, has to know which one is the ace so that the dealer can take away one that's not an ace. Okay, so the raisin has to make the choice, and then the dealer has to know which one's the ace, and then takes away the other ace, the other card that's not an ace. One of the cards that's not an ace. It doesn't matter which one. Okay, so do each of these 10 times. So, okay, suppose. Okay, so just for an example, okay, so they're all dealt out. The raisin picks this one. Monty peeks, says, okay, here's a 2. I'm going to take away the 2. And then on the stain, then we see, oh, the raisin lost. Okay. But on after we do this one 10 times, then we switch over to do this one 10 times. So dealer deals, Raisin picks one, Monty takes away one that's a 2, and then the Raisin switches. Still lost. Okay, so hopefully your Raisin will win some. All right. So anybody have any questions before you get in pairs and do this? Okay, so how about if you two can be a team, and then you have between you have 2. You have a deck of cards, right? And you have deck of cards. And you two can play 20 rounds, and you two, and am I coming up here? I'm coming up here. Okay, here. I'm sending someone up here to play. You can use these. Okay. And then we have a deck. So you can play with someone behind you. How about you two, and then you two? Okay. And then you two and you two. Right? If you need some cards, I'll get them for you. Yeah, go ahead and start. Keep a tally. I'll come around and help if you're not sure what's going on. Okay, so you have cards. You have cards.
Unless you want to do the switch one. No, I can start with this. There you go, stay. Yeah.
If you're not sure what to do, raise your hand, okay?
Okay, flip over your card.
Which one did you pick?
You're always going to have 2 cards.
Take one of the 2 cards.
So the chances greater.
Now if you want to stay back,
I mean, take away the 1 card.
did you have a
So you always have
So you lost.
We'll do one more with it, and I can do it all.
Right, because you don't take away the 8s, you take away the one that's not in the use.
Two there, the ace.
Now you have to take away one of them.
Obviously, the one, it's like Texas, or the one that is the ace. You take away the other one.
Right. Oh, sorry. I'm just like.
Excuse me.
I know.
Once you have your data collected, I'll come around and record it, okay? So raise your hand if you get your 20 rounds done.
That's awesome.
I'll just after you pick it, I'll just flip it.
See if I can start recording some of these.
One more.
What? Should have done that.
Oh my gosh.
Okay, so this time. Okay.
Stay with it.
Well, that settles it. I'm always switching. Always.
Yeah. She staged 7 times lost 7, and every time she switched, she won.
Really?
Yeah. Yep. I mean, I only got one more than so far. Not doing that.
I am too.
Now remember, you have to turn up to 2 when you're doing the switching, okay? Okay. Remember, Monty turns up a 2 when you're doing the switching, okay? If there's 2 twos, Monty takes switch 2.
Okay. I'll do one more.
One more left.
I need one more win. Fulfill my prediction.
I didn't see it.
Okay.
Thank you for playing with me.
What did you have?
We had for staying, he won 3 times and lost 7.
Okay.
And then for switching, he won 5 and
Try
lost
to
5.
do the ultimate mind game. Switch to this one. I'm gonna pick the right one this time. I have to switch.
Switch got more wins.
My eraser
Wait, I forgot what I did.
Take that one. I'm stuck with you.
She stayed with the original, she won once. When she switched, she won twice.
Okay. Okay, so I have to switch. Did I get your number? Did I get your number already?
Okay, so what's in your packet?
For state, we have 2 wins and a loss. Switching, we have 4 wins and 6 losses.
You have 3 cards, but if you take 1 or 2, it's going to be correct if you switch. So, if you switch, if you take 1 or 2, you 3 cards with a 33% chance for 66% incorrect. Because you're going to have it.
Did you finish?
Yeah.
We did. Okay, and what would you get from this?
2 wins and 8 losses. 7 wins and 3 losses.
Okay, well, what we did was an experiment looking at relative frequencies. So we have the probability of an event happening, which is a theory, and then we have relative frequency, which is the experiment, which if you have a large enough group of people, you should have your relative frequency come very close to the probability. So I'd like the first 2 rows to add these up. This is a 10, and the second 2 the second 2 rows to add these up, please. And then once you've added it up, confirm with your neighbor so that we can get a confirmed number here. You just have to add up the wins. So how many wins were there in here? Anybody have it yet?
36.
Anybody else get 36?
Yes.
Great, 36, okay. And how about here? Second 2 rows, did any of you talk to your neighbor?
61.
Thank you. So our relative frequency with staying was 36 out of 100 games between all 10 groups, or 0.36. Our relative frequency with switching was 61 out of 100. The actual probability of winning when you stay is 1/3. Or 0.33. So our relative frequency in our experiment came out pretty close to what the probability predicts that we should get. The probability of winning when you switch is 2/3, 0.67. And again, our probability in our experiment, our relative frequency, came out pretty close to the probability. So that's kind of weird. You would think, well, my husband insisted it had to be 50% for each of them. So we had a nice long argument, and then he didn't want to hear the reasons. So that didn't work. But hopefully you're going to get the reason in section 8.2. Our work in section 8.1 then was just to think about situations that jar our intuition and can lead to new and important insights. So that they jar your intuition is what hopefully makes you think about probability more closely and how is it working. Let's go in 8.2 and look some more at probability. So 8.2 opens with a question. When you roll a pair of dice, are you more likely to roll snake eyes, which is 2 ones, or 7? How many of you played games with dice? Anybody else play games with dice? Some of those games are going the way of the dinosaur here. Okay. All right. So are you more likely to roll 2 ones or a 7? Anybody know? Yeah, someone said it is 7. Why are you more likely to roll a 7?
There's more ways to make a 7.
Good. When you have 2 dice, there's more ways to make a 7. That's exactly right. Because you can make a 7 out of 2 dice with a 1 and a 6, a 2 and a 5, a 3 and a 4. Whereas to get 2, you can only roll a 1 and a 1. Those are the only options. So probability has to do with how likely something is to happen. We're going to do another experiment here with pennies. So I have a bunch of pennies to hand out. I think you only need 1 penny. So just go ahead and send the pennies down. And when you're done at the end of class, just send them back up here. If you want, you can just count out how many pennies to send down up here at the top of the wall. Okay. Or you can just set them all down if that's easier. So take a penny and pass them down if you want, and then at the end of the class, just put them at the end of the table, please. So pennies and dice are nice to do probability with because it's pretty straightforward what you can expect. Like when you flip a coin. Okay, you throw it up in the air, you flip it. You're going to get a head or a tail, right? What's your probability of not getting a head and not getting a tail? 0, yeah. So 0 probability of not getting a head or a tail. So you're going to get a head or a tail. So we do lots of experiments learning about probability with coins and dice. So what we're going to do is take a penny and flip it 3 times and record the result. So mine would be tails. So write down what you have, and then we're going to list all the possible outcomes. Actually, we're going to do that experiment again. So once you did it one time, repeat it. So we're going to do it 3 times all together. Did you know if you balance a penny on its side, it's not a 50-50 probability it'll land heads? So if you have 100 pennies and lots of time, you can try balancing them on their sides and counting how many fall on their heads. It's not 50-50. So we did 3 times here of 3 of those. Well, once you've done that, let's record all possible outcomes. So we're going to list all the possible ways that could have turned out, and I'll start with the 3 that I have. So I have tails, heads, heads, tails, 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 heads, heads, heads. Somebody tell me an outcome that wasn't any of these 3s that you got, please.
Tails, tails, heads.
Tails, tails, heads. Okay?
Heads, tails, tails.
Heads, tails, tails. Okay? Anything else?
Heads, heads, tails.
Heads, heads, tails. And what else could happen?
Tails, head, tails.
Tails, heads, tails. Did anybody have the opposite? Heads, tails, heads? Yep, okay. Heads, tails, heads. I didn't repeat any, did I? Any that I got that missed? Let's see. Okay, I think we have all of them. So let's look at this and think about what is the probability of tails, tails, tails. We didn't really talk about what probability is yet, did we? Well, when you just toss one coin, what's the probability of getting the head? Yeah, 50-50. And so as a probability, we write probabilities, that would be saying it as odds. So we're going to say it as probability, and then we use a number between 0 and 1. So we'd say 0.5. So the probability of a head would be 0.5. So you have half the chance of getting a head. And that's because you only had 2 chances, right? You had 2 chances. You get a head or a tail. And one of those that you wanted was a head. So this 1/2 was the outcome you were looking for, which is a head, out of the possible outcomes. So that is how we do probability. We look at the possible outcomes and we pick out, well, how many of those outcomes are what we're looking for here. So we listed all the possible outcomes. There were 8 possible outcomes, and of those 8 possible outcomes, only one was tails. So the possibility of throwing a dice 3 times and getting tails, tails, tails is 1 out of 8, because the different outcomes you could get, there was 8 different outcomes, and out of those only 8, only one had tails, tails, tails. Now, what would be the probability of heads, tails, heads then? With that in mind. It's exactly the same, isn't it? Because there are 8 different ways that your coin tossing could have turned out, and only one of those ways is heads, tails, heads. So that's only 1 out of 8 also. But if we change the question and we ask, what is the probability of exactly 2 heads, well, then it's going to be a different probability, because there's more than one example there that has 2 heads exactly. So how many of those different possible outcomes had exactly 2 heads? 2? Were there 2? Let's see. 1, 2. Yep. There's 3. 1, 2.
The very top.
Oh yeah, the very top. Okay, so there's 3. Good job. Okay, so then there's 8 different ways to throw a coin. You get tails or heads. But out of those 8 different ways, only 3 have exactly 2 heads. Can you go ahead and figure out what the probability is of exactly 1 tail? Anybody want to tell what they wrote? It's the same problem, isn't it? The ones where you get 1 tail are the same ones where you have 2 heads. So that was 3A also. So this is all possible outcomes with 3 coin tosses. All right, here's a harder one. So with 3 possible coin tosses, can you figure out the probability of 2 or less heads? Yeah, 7/8. So all of them have 2 or less heads, even the one with no heads, except for the one that's all tails right there. Wait, No, that one has 2 or less heads. The one that's all heads is the one that's not in there, because that has 3 heads. So we're looking at 2, 1, or 0. So if you thought, well, I didn't know you meant 0 heads, that's the problem with the question itself, not with you. Okay, so I'll try and be real clear on quizzes so that you don't make an error just because you don't know what the question's asking. Well, let's go ahead and write down formally the definition of the probability, okay? So this is just from your textbook. The probability of an event occurring.
We can't see it.
Okay, thank you. The probability of an event E occurring equals N divided by T, where N is the number of different outcomes in E N is the number of different outcomes in E, the event. And T is the total number of equally likely outcomes. Is anyone on D2L where they can open the Dropbox and see if that's what it is? Okay, can you please start writing your name next to these? Because unfortunately some people have been sharing. Okay. So the probability is what we figure out, what we expect is going to happen. We look at the total possible outcomes, and then we pick out the ones that we're looking for. For example, at most 2 heads, or exactly 2 heads, that would be E, the event. And there were 3 events, 3 different outcomes that happened with out of the 8 total equally likely outcomes. The other thing that I'd like to write down formally is the law of large numbers. If an experiment is repeated, a large number of times, then the relative frequency of a particular outcome, will tend to be close to the probability will tend to be close to the probability of that particular outcome. So we saw that with the Monty Hall scenario, and that's why we had 100 in our relative frequency, so that we could see a larger number of outcomes. Because some of you individually were winning better when you stayed than when you switched. But when we did the large number of outcomes, then it's better if you switch. And that's why the casinos can do well, because they bet on the law of large numbers here. So sure, some people are going to win once in a while, but overall, the probability, the relative frequency will be close to the probability, and the casinos will make money, even though here and there you can make a little money sometimes. Although my in-laws used to gamble quite a bit. I wish I had all the money that they gave at the casinos. But anyway, they never would talk about their losses, right? They're always, oh, I won so much. Yeah, well, how much did you spend? Well, we won't talk about that. Oh, well. Okay, so let's go ahead and put this away for now, and we'll come back to 8.2 on Wednesday. Oh, yeah, Penny's at the end of the table otherwise, okay. Please.